All right, we'll go ahead and get started. Thanks everybody for joining us this afternoon. My name's Suzanne Foss, and with me today is Adam Mollenkopf. We both work for the Real-Time GIS team at Esri. I'm a product engineer, so I focus on things like requirements gathering, documentation, tutorials, and Adam leads our real-time and big data GIS capabilities here at Esri. So this workshop today will walk you through some of the intermediate and advanced topics on implementing real-time GIS in your organization. And it's going to be about using GeoEvent Server, but also about using Portal for ArcGIS and the spatiotemporal big data store. In this workshop, we do assume that you're familiar with the basic concepts of GeoEvent, so we won't spend an extensive amount of time on introductory concepts, but instead we're going to focus on how you can avoid common gotchas with the software, how you can adapt and adjust the capabilities and sort of configure them to meet your needs, how you can maximize performance, and then how you can implement GeoEvent Server for resiliency and scalability considerations. So our discussion today, it's naturally going to start with ingestion best practices, since that's the first hurdle that you have to get past, which opens up the rest of the capabilities in GeoEvent Server. And then we'll follow up with a few recommendations on analytics. Then we're going to cover output and dissemination capabilities and what this means for how your real-time data can be visualized in maps at the end of the day. Then we'll spend quite a bit of time on the storage of your observations, since some of the newer capabilities in GeoEvent and ArcGIS allow you to store larger volumes of data over time. And we'll cover some suggested approaches for deploying GeoEvent with resiliency, which also provides the ability to linearly scale GeoEvent for some higher velocities of data. Towards the end, we're going to talk a little bit about deploying real-time GIS at a massive scale, but we're also going to touch on some of the roadmap items for 10.6. So we'll get started with ingestion and analytics in GeoEvent. So you bring streaming data into ArcGIS GeoEvent Server via an input connector. And there's a variety of these input connectors that come out of the box. These input connectors handle common data formats like JSON, GeoJSON, XML, text, and what have you. And you can use them to pull for data from a source. You can use them to receive data over a socket or an endpoint, for example. And you can also create your own connectors with the SDK. There were some sessions this week that covered some of those concepts if you had a chance to go to them, but I think they've also been recording most of the sessions, so if you missed them, you should be able to catch them on video. Our team creates quite a few custom connectors that we post on the Esri gallery. And this includes things like connectors for Twitter, for Instagram, for RabbitMQ, Kafka, among others. Most of these that we have on the gallery are based on some sort of third-party technology or other, and so we have them on the gallery so that we don't bundle them with our product installs, and then we can't update them as quickly as those third-party technologies update. So that way we can kind of update these separately from the product cycle. And likewise, we have a gallery for custom connectors for partner technologies, so things like ExactEarth, Valarm, Waze. And so overall, if the out-of-the-box input connectors aren't really meeting your needs, you should definitely check out these galleries to see if there's something else that can fit and solve the hurdle of getting your data through and into the system. So a best practice for ingestion, much like writing your own custom connector, is to actually configure your own custom, or I should just say configure a connector to do what you need and to bring in some specific data. So connectors in GeoEvent Server have two basic parts. They're made up of what we call transports and adapters. So transports, that's the mechanism for sending or receiving data over a specified communication channel. So that's things like HTTP, TCP, UDP, WebSockets, feature services. Even files are considered a kind of transport in this parlance. Adapters interpret data formats. So we have basic ones for the most common formats, as we mentioned before. And our default connectors in GeoEvent are basically made up of combinations of these transports and these adapters. And because these components are separated in this way, you can actually take these different pieces and put them together to configure your own connectors without necessarily having to write any code and develop something full-fledged from scratch. So for example, we don't list an out-of-the-box connector for receiving JSON over TCP, but you could configure a new connector, pair the JSON adapter with the TCP transport, and then you could use that to create GeoEvent inputs for your data. So definitely evaluate the available transports and adapters that come with the system if you're thinking that you need to develop your own. Take a look at what's available first and how you could configure them. There we go. So the way that you configure a connector is you can go into the site section of GeoEvent Manager to the connectors subtab, if you will, and you can edit it if you just want to adjust the available properties of an out-of-the-box connector, or if you create a connector, you'll be able to pair the transport and adapter together in that way. So any work done on connector configuration is done in this site section of GeoEvent Manager. And when you edit a connector, you basically have lots of flexibility to customize its settings. You can set its default name, you can set its description, you can pick the transport and the adapter involved, of course, and you can also update the properties and parameters that are displayed. So basically you can control what parameters are exposed to the user when they actually go to configure an input based on that connector. The other thing to note here is that these customizations to connectors, whether you customize an existing one or whether you create a new one, they're part of your GeoEvent configuration store. So you can always export your configuration if you need to make similar customizations on another machine, or if you're taking GeoEvent off one machine and putting it on another and so forth. So you only necessarily have to do these custom configurations one time, and then you can bring it anywhere you need to. Much like there are additional connectors available on the gallery, these individual transports and adapters themselves, some of the custom ones are available directly, so definitely feel free to check those out. And there's also a GitHub repository where you can find a number of them that are available open source, and you can take the source code and adapt as you need for your data. Some of these that are available on GitHub include the Common Alert Protocol adapter, the IRC transport, and then there's a couple others as well. Many of our processors are also available on the GitHub repo. So things like buffering events, calculating bearing and range fans, doing spatial queries. There's a lot of sample code and examples up here to get started if you're developing your own components. So then moving on to analytics in terms of some tips and tricks. One of the questions that we often get asked when configuring analytics in GeoEvent is how they should be designed to really be the most effective. So in GeoEvent, an analytic is called a GeoEvent service. This is what basically allows you to take your input stream, different operators and processors, to transform or manipulate the data in some way, ask a question, and then send it to an output destination or send an alert with the data and so forth. So one of the questions that we often get is if you have several different workflows as part of your overall deployment, several different analytical workflows that is, that you're trying to accomplish for different data streams. Typically the choice users have is whether or not they want to have a smaller number of GeoEvent services that are more complex and have a lot of processing steps, or if they should instead have a larger number of GeoEvent services that are individually simpler in each case. So users are often wondering which approach that they should take with this. And to a certain extent, this really does depend on the use case involved, and we recommend, to the extent that you can, trying both approaches and comparing the performance based on the computing resources that you have. But it does get interesting in particular when your continuous analytics involves spatial filters or geotagging that needs to leverage geofences. So for example, what you're looking at in this diagram here is a set of GeoEvent services. Two of them, the first two, are using the same input 1. And all of these services, however, are referencing the same set of geofences, which are called zones. So each of them is doing a spatial filter against this geofence category called zones. And then this second GeoEvent service is also employing a geotagger step against those geofences. So this configuration would be less than optimal because the geofences are being stored in the cache multiple times. They're being stored in the cache for each GeoEvent service, and that is taking up additional RAM that you don't need to be consumed. So for this kind of a situation, the optimal approach would be actually to combine everything in one GeoEvent service. And so in this case, yes, it's a little bit more complex compared to what it was before, but the zone geofences are only pulled into the cache once, and they can still be applied at all the different steps in that service as needed. So in this sense, we just have now one kind of pipeline that splits into two for input 1. It gets the filtering step, and then it's either buffered and sent to output 1, and then it's geotagged and sent to output 2. And input 2 has its own processing flow, which isn't connected to anything else, but that's still a valid approach to have in the same GeoEvent service. Different inputs can definitely be part of the same service. You don't need to think about isolating them in that way necessarily. All right, so next we're going to move on to tips and tricks for dissemination of your real-time data, in particular because this affects your options for visualization. So similarly to input connectors, you use output connectors to disseminate your real-time data in various ways. The out-of-the-box output connectors in some ways mirror the input options. You can push GeoJSON or JSON to a website. You can write to a file. You can also take different kinds of actions. You can use several connectors that support alerting, like sending an email, a text message, or an instant message. And to visualize your data spatially in ArcGIS clients, you would add or update a feature in a feature service, or you could write that feature to what we call a stream service. And we'll come back to those options in particular in just a minute. But overall, much like with the input connectors, if none of the default output connectors work for you, then again, one best practice is to check the gallery for other available custom connectors that might be available. And again, you can build your own connectors with the SDK. Some of the example connectors in the gallery for output is writing to Hadoop, pushing events to a Kafka broker, pushing events out to RabbitMQ, and so forth. And of course, much like input connectors, output connectors are also based on transports and adapters. So you don't necessarily have to develop your own. A best practice is to pair an adapter and a transport together. And so, for example, our output connector, one of our output connectors that's out of the box is to send an email. And this is simply made up of an adapter called the message formatter and a transport for SMTP. One interesting configuration that you can do with GeoEvent with transports and adapters is to combine the message formatter with the HTTP transport. And that would allow you to actually make a call to a geoprocessing service at the end of a GeoEvent pipeline. And maybe trigger a more in-depth analysis based on conditions in your data. Naturally, you'd want to keep an eye on how often you're going to make that call to the geoprocessing service based on your real-time conditions, because geoprocessing services will take, of course, various lengths of time to finish. So you wouldn't want to be calling on it for every single event if you have high-velocity data. But it's an interesting example of how to configure a connector that sort of extends your overall capabilities of what could be the next step in a real-time chain. All right, now if disseminating your data needs to include geospatial visualization, there's basically 5 out-of-the-box output connectors that you can use. You can add to a feature service, you can update a feature service. Specifically, you can add to a feature service in the spatiotemporal big data store, and update a feature in the spatiotemporal data store. And then the 5th one is that you can send features to a stream service. So there's a few ramifications for visualization options based on which one of these you choose. So let's go ahead and explore those in more depth here. The first thing is that there's a couple key differences between the way stream services work and the way feature services work. So stream layers are a JavaScript implementation, and the way they work, for that reason, they work only in web applications that are based on the JavaScript API. So in the web application, you have what you call a stream layer, and that stream layer subscribes directly to the stream service, which means that it receives any new features immediately. The map is in basically listen mode. And there's no middleman, if you will, between GeoEvent and the actual map. So you have low latency for that reason. But the flip side of this is that there's no database involved. So you can't take a stream service and play it back over time. It's just that map receives the feature is on the map for the duration of that session, and that's kind of the end of the story. Now, feature services, on the other hand.
One comment on the stream layers. So the Pro team is actively working on supporting stream layers inside of Pro as well, so that's expected to drop at Q3 later this year. So probably in the 2.1 release of Pro.
Okay, that's good information. So moving on from stream services, just for this case and contrasting them, feature services are specifically designed to visualize data that's in a database. So when you display a feature service or a feature layer on a map, you're actually polling that database. And that polling might happen, I think as most of us would be used to, just every time you pan and zoom the map. But you can also set a feature layer on a refresh interval so that you poll regularly. Now, the backing of a feature service could be either an enterprise database, it could be the spatiotemporal big data store, or the feature service could be hosted in ArcGIS Online or Portal, in which case it's essentially in the relational data store. And to get updates from this, again, you'd have to periodically pull data, and your app could handle that, or you can set the property on the layer item in the web map viewer and so forth. In this case, though, because data is stored, you can actually play it over time. Now, when you store features in the spatiotemporal data store, you can also visualize your information as a map service, which automatically aggregates your data on the fly. If you've been to some of the other GeoEvent sessions this week, you may have seen some examples of this. It was certainly shown in the plenary as well. And this allows you to really visualize large volumes of data effectively. So adding or updating a feature in the spatiotemporal big data store is a good connector to use if you expect your data to accumulate over time and you want to be able to explore that data. Also, when you store data in the spatiotemporal big data store, you can use geoanalytics tools to do batch analysis in an ad hoc fashion against that data. And geoanalytics also writes back to that data store as well for results. So the long story short with visualization options is that if you need to store data for analysis or temporal playback, then you want to use one of the output connectors that captures data to a feature service. And if you want really, really rapid visualization, you'll want to use the output for sending features to a stream service. And you can do both. In a lot of cases, we have clients that will write to the spatiotemporal data store so that they can archive their data and always go back to it later. But the active layer in their map is the stream service so that they can see features immediately as they come across. So overall, what we're going to walk through here is the best practice workflow in GeoEvent to take streaming data, or just real-time data, if you will, of any kind and visualize it on a map. So at the high level, the first thing that you're going to want to do in GeoEvent Server is create an input for your real-time data. And part of creating an input for the real-time data is defining the schema. GeoEvent needs to understand the schema of the data in order to parse the message and then be able to operate it on it in real time. So a GeoEvent definition essentially captures and allows GeoEvent to understand the schema of your data. After that, you'll create an output that uses a connector that either adds features to a stream service or to a feature service in some way. Those, again, are your output connectors if you want to visualize your data. And if you're using one of the later versions of GeoEvent Server, you can actually create those, the feature service can be published on the fly as part of GeoEvent Server, which is a slightly newer capability for regular feature services. And third, you'll connect your input to your output using the GeoEvent service. A GeoEvent service can be as simple as input goes to output if they have the same schema. You can also define the additional processing steps that operate on the data as part of the GeoEvent service. The GeoEvent service, as many of you may be familiar, is sort of a real-time model builder. And then once you have your GeoEvent service configured and all three of your components have started and data is flowing, you'll basically be able to add the corresponding layer, whether it's stream or feature or map, to your web maps and begin to visualize the real-time data in your applications.
If you're a historic GeoEvent customer, you may have heard previous presentations. Can you go back?
Oh, yeah.
Where we talked about two different patterns. So if you're working with traditional feature services, you would first start with ArcMap, create your feature service, publish it, those types of things. New at the 10.5 release, we now support this workflow Suzanne just described for the full path. So if you want to publish a traditional feature service to a relational data store, you can do that now through the GeoEvent Manager. So you no longer have to go create an ArcMap first, publish it, and do other things. So we've really streamlined that process to be a consistent workflow.
You can kind of go through the whole workflow just using GeoEvent now as opposed to having to leave and use different applications, as Adam said. Okay, so with that, we're going to move on to storage, and I'll hand it over to Adam to cover best practices for storing your data over time.
All right, thanks, Suzanne. So I'm going to talk about storage. This is primarily going to be focused on the spatiotemporal data store. I'm going to give you some best practices and some guidelines for this, but there is a session just following this that's going to deep dive into the spatiotemporal data store and use cases with GeoEvent and GeoAnalytics using the spatiotemporal data store. It was introduced at the 10.4 release, so it's been out for some time. We've significantly enhanced it at 10.5. One of the things that I commonly get asked is what's the licensing for the spatiotemporal data store? So as long as you have an ArcGIS enterprise and a portal environment inside of your organization, you can deploy as many spatial temporal data store nodes as you like. There's no additional licensing for these nodes. So if you want to deploy a 100-node cluster, you can certainly do that. It's not going to cost you anything from a licensing perspective. It's just the hardware that would need to be put in place. So it purposely has lowercase letters that kind of indicates that it's a component of our platform. It's not a product. So the spatial temporal data store you can think of as just a component of our platform, not a product offering. The other common question I get is, so how do I set up my topology, or what does the deployment environment look like for this? So for development purposes and just research purposes, if you want to just try these things out, you can certainly put all of this on the same machine. But when you start to get into deploying this and fielding this to production, what we highly recommend as a minimum environment is to isolate each of these machines so that they are isolated for their specific purpose. So ArcGIS Enterprise being a single machine that's hosting your catalog of information, your security model, your users, everything else that's associated with your organization. To have a functional GeoEvent server that's mainly focused on real-time GIS. And so that keeps it available for processing data in its most performant way. And then a dedicated machine for spatial temporal big data store, or more than one machine, as you'll see in a second. And then also GeoAnalytics server should be on its own isolated machine as well. The reason for this is the way that resources are used on the machine from all these different pieces of software. So GeoEvent server itself is very CPU and very network intensive because there's data flowing over the network all the time. And we are very CPU as well as potentially RAM intensive if you're doing lots of geofence detections or pattern of interest detections inside of your streaming analysis. And so that's directly in conflict with spatial temporal data store and GeoAnalytics server. So if you were to issue a GeoAnalytics job to go run and do analysis, it's extremely compute heavy. So it's going to consume all of the cores available, all of the RAM available to do that. So if you were to run those on the same machine, your GeoEvent server would work fine until you ran a GeoAnalytics job that might take 3 or 4 minutes. And for those 3 or 4 minutes, GeoEvent's going to suffer because you're contending for the same resources. So it's a best practice not to deploy those on the same machine. Certainly if you're just doing staging or development and proof of concept things, you can certainly put them on the same machine, but plan an environment that isolates these out. And then additionally, in the spatial temporal big data store, it's very CPU intensive as well, because as we write data into the big data store, we do lots of indexing so that we can quickly retrieve the data. We're indexing potentially up to 4 spatial indexes, depending on what aggregations you enable. We're also indexing on the temporal field, the temporal dimension of the time field, and then also doing an inverted index on all the other attributes. So this is what allows the spatial temporal data store to have super fast query response time. And we're going to deep dive into that in the session following this in the spatial temporal data store if you're interested in more details on that. So it's very CPU intensive because of the writes that are happening, and those are continuously happening in a real-time system. But it's also very RAM intensive too, because it tries to keep in memory what's been frequently accessed. So whatever's been hot or accessed recently is going to be in RAM. So instead of having to go all the way down to disk to get that data again, the second clients that connect would get things that are hit inside the hot cache that's available inside of RAM. And so for a real-time system where you have clients polling every so often to get new updates, that's very important to keep that cache hot so that we get really quick response times. And so that's how you see the aggregations happening so fast and the other things that are happening in the visual displays with the map services and the feature services. So keep this on isolated machines where you can. If you're really in the real-time and big data space, this shouldn't be a shock to you, but our recommended environment for folks that are doing this for real and you actually have very high volume data, very high velocity data, I'll qualify that with high velocity data being, hundreds of events per second or more, or if you have, high volumes of data that you want to store over time. So if your customer or your organization or your boss has said, I want to keep the data forever, we have no retention policy, just keep it in there forever, then you're going to need a concept like a spatial temporal data store over time as you start to record these observations and they consume more and more disk. The spatial temporal data store is you can think of it as a geodatabase, but that spreads across multiple machines. And so it's based on NoSQL technology, it's based on other things. Elasticsearch is what we use underneath it. But it allows you to grow a database extremely large. We've tested hundreds of nodes of clusters. These have been tested in industry much larger than that as well. So this can scale out as big as you need it to. A 3-node cluster is what we recommend as kind of a starting point because of the way that data is replicated across the cluster. So when you write data into the spatial temporal data store, you can configure what the replica factor is. So you can say, I want to replicate every write to one other secondary node. And so in that case, if your disk fails on one of your nodes, you don't ever have data loss. So there's always continuous access to the data. If you have a 1-node big data store node, you can certainly do that if you want, but if your disk fails, then you're kind of out of luck until you go restore that. We do have snapshotting and other things available that we'll talk in more detail in later in this session, but those snapshots would allow you to restore the state of a cluster that went out of chaos or something. But if you had a single node, you could restore from a snapshot onto another node and not lose your data, but you would have downtime. So we suggest an N+1 architecture where N is we would need at least 2 machines to keep things highly available, and then we have a +1, which is a 3rd machine. You can certainly get by with 2 machines, but 3 is what we recommend. The GeoAnalytics server is a little bit beyond the scope of this topic, but I'll just mention it briefly. You want to at least have as many nodes of GeoAnalytics as you have the big data store nodes, and that's if you're working with data primarily in the big data store node. So the way that GeoAnalytics parallelizes its algorithms and its analytics down to the data is in such a way that it needs to be coordinated with the spatial temporal data store. So if you have 1 GeoAnalytics server and 3 big data store nodes, you're not really going to be able to parallelize very well. So you want to at least have as many nodes as you do in the big data store, if not twice as many nodes, because the GeoAnalytics server can do computation faster than we can I/O the data out of the big data store. So that's just kind of a best practice for deploying a production environment. And if you're not in the high volume, high velocity scales, you certainly could kind of go with our minimum environment, but just know the constraints that I mentioned before. As far as operating system requirements for the spatial temporal big data store, this is all documented in the links down below, but this is just kind of your summarized guide here. We support Windows and whatever flavor of Linux that you desire. So we always recommend using the latest version. That's where the majority of our testing happens. As far as certification, when we release 10.5.1 and other types of releases, it's usually on the latest updates of each of these OSs. We do limited testing on the older releases, but we ensure that the latest version of these OSs are up to par. 64-bit is required for this environment. So you'll need a 64-bit OS, either Windows or Linux. And then just one note on the Windows environment is that underscores are not allowed in the machine names when you define the name of your big data store. As far as resources and how you should plan your profile of what these machines would look like, 8 cores is a minimum requirement. I think 4 technically is a minimum requirement for that, but there's not really 4-core machines that are around anymore unless you're in a virtual environment. But the spatial temporal big data store is not a licensed component, so you're not paying per core. So you might as well put this on as many cores as you can because it's not costing you any licensing for this. It's just the hardware cost. The more processors you have, the faster write and indexing time you're going to have when we're writing data into the spatial temporal data store. So this will affect your latency of when do you get data, when do you write it to the big data store, when can you see it on your operational displays. It's typically very fast, but if you're dealing with high velocity data, hundreds, thousands of events per second, then more cores is certainly better. This will also produce faster query response time as well. So we're continuously writing data into the big data store, which is indexing and doing all kinds of things, but we also have queries that are hitting the database at the same time. So the more cores you have available, the better. So 4 or 8 is the minimum and 16 is the recommendation. And we will certainly use all of those cores if you put those on that machine. As far as storage, 400 gigabyte is, a lot of the minimum requirements here come from ArcGIS data store, and ArcGIS data store is comprised of a relational data store, a tile store, and the spatial temporal big data store. So when you see the minimum requirements on these links here, this is kind of describing it in a general fashion for ArcGIS data store, so it's the least common factor between those 3 different types of stores. But when you're working with the spatial temporal big data store, the whole purpose is that you have high volume data. And so typically you want at least a terabyte or more of disk space available, and that would be, you know, persistent disk that's available. It's not an ephemeral disk or something else that might be on a cloud environment. So if you're in a cloud environment, you want to attach premium storage onto these nodes. Don't use ephemeral, because ephemeral is exactly what it sounds like. If that node goes away, all that data gets lost as well. So SSD is much better as well. So if you have a choice in the matter of what disks you're going to use, SSD is a magnitude faster than spinning disk for the writes as well as the query and the access into the data. As far as memory, we allocate half of the available RAM on the machine by default to the spatial temporal data store. So if you have a 32 gig machine, we'll allocate 16 gig. You can go in and tune that to be higher if you want. We don't really recommend to tune it higher than half of the RAM available on the machine, because there's off-heap things that are happening as well. And so if you tune it to, say, you've got 32 gig and you tune it to 30 gig, you're not going to have any space for off-heap memory. And we make use of off-heap quite heavily for the caching and the other things that we do in the big data store. And if that didn't make sense, grab me afterwards and I can explain that more. The more memory you have, the higher the likelihood of your query cache hits, and you don't want to go above 32. So we've had some clients that have bought, you know, 256 gig of RAM machines, and that's not going to do you any more good. So it's better to add more machines that are 32 gig than it is to add machines that are bigger RAM, because we really can't utilize anything more than 32 gig anyway. So if you had a 64 gig machine, we would make use of 32 of that with the off-heap using the rest, but there's a bunch of limitations inside of the Java virtual machine that don't allow us to go bigger than 32 gig. That's the current state of how this is. As far as the number of isolated instances, 1 is what the minimum is, but 3 is certainly going to give you better availability of your data. So with 1 instance, you risk the chance of data loss. And if you have 3 instances, these replicas that I was describing before are written that increases your availability of the data. And the number of instances, you know, should be kind of defined and capacity planned based on the velocity of your data as well as what your retention policy is. So if you know you need to keep 6 months worth of data around and you're getting 1,000 events per second, and you know the size of the data, you can kind of guesstimate how big of, you know, disk you would need on each of the big data store nodes, and then how many machines you would need for that. And we could certainly help you through that process if you want to plan a capacity plan for either your clients or yourself. Just reach out to our team and we would be happy to help you with those plans. As far as the way data gets written into the spatial temporal data store, I'm going to kind of go under the hood a bit of what happens in the big data store, so this will give you a better understanding of how it operates. It's not critical that you understand all the aspects of what I'm going to go through here, but it'll give you a better understanding of how to use the big data store in a best practice way. So when GeoEvent writes data into the big data store, if we had a 1 node solution, we would obviously just be writing all the data to that 1 node. But if we have multiple nodes, it's a distributed database. And so we're not writing all of the data to all the nodes. We're writing part of the data to part of the nodes. And we're replicating the data across other nodes so that we can have good availability of the data. So what happens here is per layer or per data source that you put in a data store, you can define a replication factor. So what the replication factor means is the R equals 1 means we have a replication factor of 1. So that means every time I write data into the big data store, I'm going to write a primary and I'm going to write a secondary of that data. So for this T1, we'll call it track 1. This might be a phone record or something else that's coming in. And so I've identified that as track 1. The way we partition or shard data around the cluster is that we create a partition algorithm that says these T1s should always go to node 1, and the secondary for T1 should always go to node 4. That way all the data is, you know, local for that specific track. So if you're doing very specific track things like reconstruct tracks or other things with geoanalytics later on, you can get super fast execution of the analytics because all of the data for that track is local on the same disk. So we partition by track by default. That's the only way that we partition currently. We are, you know, open to making that pluggable if there's use cases that you guys have that would be beyond that. If there is no track ID or some identifier on the data that's coming in, it's a randomized partition. So it would just randomly go to different nodes. As we write T2, we get a primary and a secondary, the primary being the bigger square with the bigger font. And then we have a track 3 that's in here. So obviously there might be, hundreds of millions of different tracks that are in here. And so you could kind of see how this would spread the data out over the thing. And so if there's a failure in the cluster, so this node entirely fails, so the network got disrupted on that node, or the disk failed, or something else happened, we would need to actually, take care of T1 and T3 somewhere else. And so T1 was a secondary down on node 4, so it becomes the primary. We establish a secondary somewhere else on the cluster, and then we establish any secondaries that were on that node as well. So all of this is automatic. You don't have to worry about setting this up or configuring this. This is just the way the spatial temporal data store works. And so the replication factor is important. If data is really important to you, you might consider increasing the replication factor up higher. If the data is not important at all and you don't really care if it goes away, you can certainly set that to 0. The higher the replication number you set, the more overhead's going to be involved in writing the data, because we're basically writing that record twice with a replication factor of 1, 3 times with a replication factor of 2. Another factor on the big data store is data retention policies. So this was added at the 10.5 release. This isn't available at 10.4. This is configured per data source. So if I have good guys and bad guys, and I want to keep, maybe just a month's worth of good guy data around, and I have bad guy data that I want to keep around for 3 years, then I can set those retention policies on those features of those data sources inside the big data store. And so once the retention cycle is hit, we automatically will purge out the data that's older than that. So if you tell us to keep, I think when we showed the plenary demo, it was keeping like a week's worth of data around for the flights. And so we were getting in hundreds of events per second, but they only had like a 3-node BDS cluster. BDS is what we call the big data store internally, because it's too long to say spatial temporal big data store all the time. So we just call it BDS. So they had a 7-day retention policy on that layer. And so that's all automatic. You don't need a DBA to go in and truncate these things. We just take care of that for you. This will really help you capacity plan how big your big data store cluster needs to be as well, because you can ensure that I'm only going to keep 7 days worth of data or 7 years worth of data in this cluster, and I know how much I'm getting and accumulating over time. There's also this concept of rolling index. So the way the big data store works is each data source is spread across all of these nodes. And so I might have a data source called good guys, and each of those nodes will have its own local index of the data that's been written to that node. And so that index could grow gigantic over time if we didn't have the concept of a rolling index. So the concept of a rolling index is that we actually roll smaller indexes over time. So if your data is coming in and it's a result of GeoAnalytics server and it's never going to change, it's just static, then you could have a rolling index option of a year. And so we don't really ever need to roll that index because no new data is going to appear. But if I have data streaming in at 2,000 events per second, and the data is constantly going to be doing that for months at a time, I don't want to have an index that's months worth of data for that. I want to have a rolling index that's maybe on a daily or an hourly basis. So every hour I'm actually rolling over to another index. Having more indexes allows us to hit the indexes in parallel so that we can do really quick queries. So that's what this rolling index option is. So if your data is very high velocity and high volume, then you want to have something like hourly is your rolling index option. If your data is pretty slow, it's maybe 10 events per second, and the data is not growing that large over time, you might have a weekly or a monthly type of setting. So you kind of have to play around with this a little bit. It's a teeter-totter of how fast do you want your queries versus how fast do you want your writes. So that's just something you can play with. The general rule is to keep it low if you don't know. So if you don't know, keep a daily or a weekly rolling index, and we'll optimize ourselves amongst that. The next thing is also a 10.5 specific thing. So in 10.5, a lot of our customers were saying it's great that you have this replica factor, but it's not good enough for me as an enterprise organization to just count on that replication factor. What if the entire cluster failed? Then I don't have access to my data. So we created the concept of a snapshot, which snapshots the entire state of the cluster. And so the first snapshot will take a decent amount of time to build. If you've been a 10.4 customer using the big data store and then you upgrade to 10.5, we will be building a snapshot that's all of your data from the past. And so it'll take some time to actually build that snapshot. Every snapshot after that is incremental. So as you can see down below, this is creating a snapshot every hour. So every hour we capture whatever data was accumulated in the big data store, and these snapshots could be used to restore another cluster. So you could go create another 5 machines, and you could say restore from this snapshot, and your data would look exactly the same as where you left off. So these snapshots give you kind of a full state of your cluster in case something catastrophic happens. Now the best practice for these snapshots is obviously don't put this where your cluster is running. You want to put this somewhere else. So if that part of the world got hit by something catastrophic and we can't ever access that again, if your snapshot was there, then you don't have access to your snapshot either. So you want to put your snapshot somewhere else. Good places for this are what we support at 10.5 are Samba mounts or NFS mounts. And so put that somewhere that you have redundancy as well. At 10.6, we'll be adding S3 and Azure Blob Storage as options for you to put those snapshots into as well. But for right now, you have to use an NFS mount or a Samba mount. By default, it's a daily snapshot. If you want to increase it or decrease it, you can go in and configure that. So choosing an object ID option is kind of an interesting topic. We have this screen here that's extremely misleading, and we changed it at 10.5 one because it caused nothing but confusion. So when you read this here and it says, what's your object ID strategy? There was an attempt to actually, support 64-bit object IDs throughout the platform after 10.4. That attempt didn't pan out, and so the labels that we had in the dialogues here don't match with reality of what actually happened. So ArcGIS in general is a 32-bit object ID system. And what that means is that it's limited in how many, how big the number can be for the ID. So at 10.5.1, we've switched this to be just simply int64, int32, and string, because what we had before was completely misleading. That means that if you're using 10.4 or later, int64 should be supported. And if you opened up a layer that had int64 object IDs in it in desktop, it's not going to have a good experience, otherwise known as it's going to crash.
Yeah, one note here is it doesn't necessarily always crash, but you'll notice things like if you use object IDs that are based on int64 in Pro, it'll come into Pro, it'll probably display the features up to the object ID that's past the 32-bit size. And you'll run into it when you open the feature service table, for example. You'll run into it if you do a query against the feature service in Pro and your query is returning features with those higher object IDs. So it doesn't necessarily crash Pro outright, but it has some of those limitations.
So you might be thinking, well, int32 is fine for me, that's no problem. Well, here's just a scenario. So int32 max value is 2 billion and something there. And so all of our clients support that Pro Desktop Ops dashboard. So if you had 1,000 events per second, you'd run out of int32 IDs in 25 days. So I don't know how big your velocities are, but a lot of our customers have velocities that big or larger. And so it becomes a problem in 25 days. So for the first 25 days, they're looking at things in ArcMap and Pro and everything's going well. And then the 26th day crashes start happening like Suzanne was describing. It's like, what happened? I didn't change anything. What's going on? And it's because these IDs exceed what those clients can support. So what you have to do is, our default is int64. When you set these things up, you would have to change it to int32. And it's assigned int34 or int64. And so this gives you about 9.2 quintillion object IDs. So the current apps that support this are JavaScript and any custom apps that you build inside of runtime or JavaScript that would make use of, actually it would just be custom apps in JavaScript. So the runtime, Pro, and those things don't support anything other than int32 at this point. And so that gives you quite a bit more time to worry about the problem happening again, but it still will happen at some point. And then there's also another option that if you don't ever want to run out of IDs, there's this unique string ID. And that's actually the most optimal way to write data into the big data store, but it's limited in what clients can support that. And it's highly unlikely that Pro and Runtime would actually support a unique string ID concept in the future. It's more likely that they would support int64, but I don't have any commitment for what the timing of that is. So resiliency and scalability, this is the last topic. So we introduced at 10.3 the concept of GeoEvent clustering. This did not go very well. probably people in the crowd laughing about that had that experience. So it was observed to be very brittle and it was very subject to failure, and it required at least 3 nodes in a cluster, and the first question we always got was why 3, why can't I do 2? And so there's a number of reasons for that that aren't worth going into here. But when a node goes down, it needs to be brought back as soon as possible. That was one of the assumptions that we made. A 2-node cluster can cause what's known as a split brain condition. So the way the cluster was implemented for GeoEvent was that we shared a distributed config store between the machines. And so since it was distributed, we had to kind of agree to what the configuration was. And when there's 3 machines and there's 3 people in a huddle, you can agree to something because 2 people would say this is how it is, then the other person would say, I guess that's the way it must be. But when there's 2 people, it's kind of like I say it's this way, you say it's this way. Who's right? We don't know. And so that's what's considered a split brain condition. That's why we needed 3 nodes, and that's why you needed to bring back something as soon as possible. Those were not good assumptions because people would let their 2-node clusters keep running. We also had explicit constraints that you had to have physical hardware, and that virtualized was not a good environment because virtualized had non-determinism and network usage and other things. Which is the last bullet, which is the network needs to be stable. So if these machines can't talk to each other, then they think that they're existing on their own and the cluster's gone away. And so it makes the membership changes happen in weird ways. Basically, this proved to not be a good viable solution, and we've since deprecated that now officially at the 10.5 release. So we'll likely stop supporting clustering at the 10.6 release. We have some plans on how we're going to address this going forward, and that's what I'm going to kind of walk through here. But I want to explain some of the constraints of this option as well. So GeoEvent clustering in general should be avoided and discouraged. So if you want to do high availability or resiliency, or want to add additional scalability for GeoEvent, you should be deploying this in an isolated way. So you should have your own site around each GeoEvent server, and you should federate that into your portal. This is true since the 10.3 release and beyond. It will continue to be true at the 10.6 release. So the way that looks is each of these GeoEvent instances would have their own site, and it needs to share a common configuration manually. So we have really good mechanisms to do that because you can go into GeoEvent Manager and say export the config, and then you can go import that config on another GeoEvent. So that's actually quite easy to accomplish. The thing that's not so easy to accomplish is that for GeoEvents to work in that way, we need to have some type of event source that's feeding us data into all the different GeoEvents, and that needs to be a common event source. So the way to do that is you have to kind of bring your own message broker at the 10.5 release and before. And this message broker can be any one of Kafka, RabbitMQ, or ActiveMQ. But the look I usually get when I describe that to folks is what's Kafka, what's RabbitMQ, what's ActiveMQ. I don't want to deal with that complexity. So at 10.5, if you want to do this, you have to bring your own. We'll talk about some 10.6 things that we're going to do so that you don't have to deal with that in a moment, but that's currently what you have to do at 10.5. The other aspect of this is that when we have multiple GeoEvents listening to a common message broker, they're competing to consume events off of that message broker. So it's an active-active setup. There is no active-passive setup that's available, and that will continue to be the path forward. Active-active is the only viable option that we see is a reliable approach to this. So here's an example of messages passing through. So if I have 2 GeoEvents that are in their own sites, and I have an event that's flowing through this message broker and it's for planes, I might get that on the first GeoEvent. And I get an event 2 that comes through, and it's for planes, that might go to the next GeoEvent. But if I get event 1 that comes through again, depending on how my message broker is configured, that might go to machine 2 or machine 1. So this causes some challenges because if you have stateful processing inside of your GeoEvent, like I want to know when plane 1 enters a geofence, well, the state for the last position was on the other machine. So there's some tricks you can do with your message brokers to actually make sure that the same events for the same tracks go to the same GeoEvent. But those are things you have to configure within the message broker. So there's a couple known constraints with this option. The first is it doesn't really support the failover of state. We can support state inside of these independent GeoEvent servers as long as the message broker is configured such that all the same tracks go to the same machines all the time. But what's not supported is if GeoEvent machine 1 died and it had its state of what happened previously, If it died, then those events that used to go to it are going to go to another machine, and that machine is going to have to rebuild all that state. So there's a point in time where we might, not detect a enter condition or something of that nature because we didn't have the history to detect those things. So that's a known constraint of this. Also another couple known constraints for 10.5 and setting up your own message broker is that you need a team of people that actually know how to do that. So you can certainly hire Esri professional services to do that. I can tell you right now we don't really enjoy doing that, so that's not really something we want to do, but it's something 10.6 is going to address. We can certainly do it for you, but I don't think your IT staff would really enjoy doing that either, so it's really not a great solution. But also, input to GeoEvent is the message broker only, so you lose all the flexibility you had with all the different input connectors Suzanne went over before. So the only input into these GeoEvents is the message broker. So this is kind of a crappy situation to be in. So I'm going to go through a couple other things about stream services, which are unique to stream services, and then I'm going to tell you our answer for how we're going to address this. And it's a 10.6 thing. If you want to do it at 10.5, you have to do the things I was describing before. An isolated deployment of GeoEvent leads to some challenges with stream services. So stream services are a capability of the platform, but fundamentally they're connected to a GeoEvent. GeoEvent is the thing that's the provider of the stream services. So when a client connects, if it's a JavaScript client or whatever the client is, it connects to a stream service and gets a socket connection, a WebSocket connection into a GeoEvent container. And so when data flows through here, we can get, event 1 gets passed through, but if my clients C and D are connected to that same stream service with the same name, same everything, but it went to that other machine, they don't get number 1. So that's depending on how you've configured your message broker. So if 2 comes through, these guys get 2. So you can configure your message broker, Kafka and RabbitMQ and ActiveMQ all have setups that will allow you to actually fan that out to all of those machines so they can all get the same events. But the challenge there is when we're getting those events and 2 GeoEvents, if you're doing, send an email when this happens, you're gonna get 2 emails. So you kind of have to figure out how you want to balance these things around. So when you're working with stream services, keep that in mind, that's kind of the approach that you have to take with stream services, is that you're duplicating those events across multiple GeoEvents, and you'll have to know if you're trying to alert or do things, you'll want to attach that to a different GeoEvent service path than the one that's actually emitting to the stream service. So you might be doing some duplicate analytics inside your GeoEvent services, but it's for a good purpose because you don't want to alert more than one time. So there's workarounds to achieve that, but be aware of that is a challenge, because I would hate for you to set up a GeoEvent and then your customers are like, why am I getting duplicate alerts? So the last comment on stream services is if the clients can be set up in such a way so that they don't know the IPs or the host names that they're connecting to for the stream services. So this is a typical setup if you don't want to expose your IPs or host names out to the public world. So if you're hosting like a weather provider information and you want clients to connect and get real-time weather events and other things, you don't really want them to know that there's 2 machines called A and B. You want them to connect to a reverse proxy. And if in this case, all of the events would get passed to those clients. But if this machine dies here, if we didn't have the reverse proxy in place, client C and client D really wouldn't know what to do at that point if they were connected to that. But with a reverse proxy in place, we automatically switch client C and D over to another machine. So that allows us to accommodate that. So this is really complex, Adam. This is, okay, you went through a lot of concepts and there's a lot of constraints. So how do we simplify this? Well, the answer, and fortunately or unfortunately, depending on how you look at it, is that we're going to address this at 10.6. And the way we're going to do this is that this is the picture I just described to you, where you bring your own message broker and it sits in front of GeoEvent Server. We've purposely been denoting GeoEvent Server with 3 different icons. And that wasn't, just because we randomly did that. That was actually for a purpose. And that purpose is that at 10.6, we're actually going to decompose GeoEvent so that those become spread out across another, so that we can actually deploy this in an environment that looks something like this. And we're decomposing GeoEvent Server such that that little gray thing, we never really explain what those icons are. The black is the inputs of data coming into GeoEvent. The purple are the GeoEvent services. Internal to GeoEvent Server, we have an event hub that we use internally so that we can route when something comes in on this input, there's 15 GeoEvent services that want that event. And so we route those to those GeoEvent services. So we already have an event hub and we already make use of it internal to GeoEvent. What we're doing is replacing the need for you to bring your own event hub and basically bringing it into as a product component, another lowercase lettered thing that you can put in front of GeoEvent Server. So when you deploy GeoEvent Server at 10.6, when you do the installer, you'll get the option of what do you want to deploy, GeoEvent Server in a traditional way, which would look something like this, or do you want to deploy your event hubs on different machines from GeoEvent or your connects. These are not the terms we're going to use for 10.6. I'm just using those as placeholders for now. But your ingestion nodes that would sit in front. You won't have to license the Event Hub nodes. You won't have to license the Connect nodes. You'll only license the GeoEvent Server nodes. So there's no different licensing with this. It's just allowing you to, instead of having to bring your own message broker and have to know all those details I just went through, we're going to hide all those details from you. So if you have a stream service connected, it'll be configured right that it actually gets the events correctly. If you want the behaviors we were talking about, we would configure those appropriately. So what I think most people are going to do is they're going to set up their environments to look like this at 10.6, where they'll run the event hub on the same machine as the GeoEvent server, and you could actually run the connects or the sources or input connectors, whatever you want to call them, on different machines. This actually allows a nice place for firewalls to sit in between and other things as well. So this is going to be the predominant model, or this will be the predominant model for folks. But we give you that message broker without you having to bring your own, and we solve a lot of those complexities. We are going to embed Kafka inside of the event hub. So we're going to take care of all those details. You don't have to know Kafka at 10.6. We'll just embed it and abstract it away from you. And so we'll take care of that for you. So this hopefully will be a better answer for folks to stand up resilient things over time. So we've been talking a lot. I think we've gone through a lot of best practices. I think it's time to open it up for Q&A. We have 4 minutes to take any questions you have or any feedback. Was this useful? Yeah? Okay. Yes, sir. So the question is the big data store and virtualization. So in general, I mean, you can do that if you want. The comment I would make is virtualization usually means non-deterministic behavior sometimes. So if you are in like an Amazon or an Azure environment where you have fairly isolated virtualization, then that's going to work great. And we do that all the time. We're standing up stuff on Amazon and Azure all the time. If you're running in your corporate virtual environment that's, you might be running on the same machine as some other CPU and RAM intensive thing, then you're going to get non-determinism. So it's best to use either physical hardware where you can internally, or if you can use Amazon or Azure or some deterministic virtual environments, those are better. Yeah. Yes. So the comment is, on the big data store, would you agree that you get better performance on Linux than Windows? So I think there's incremental performance improvements on Linux. It's not significant enough that I would say one or the other. But in general, Elasticsearch, which is what we use, works better on Linux, and it'll perform faster. So it's the typical benchmarks that you would see on an Elasticsearch deployment on Linux versus Windows. So it's incremental, within 10% kind of range. It's not, a 80% gain or something like that.
Okay.
Yes.
Are there benchmarks available to know exactly what you need for a certain number of events and offenses?
Go ahead. You want to cover that one?
Yeah, sure. I was going to say
Can you repeat the question?
Oh, sorry. Yeah. So the question was, are there benchmarks available to understand how much space you need to store your data? Do I have that right?
CPU and RAM the number of events and number of GeoEvents that you can handle with a certain machine.
Okay, yeah, so the question includes, the CPU and the RAM that you would need to handle different combinations of things. The general answer is that I think we have some very basic numbers, but it depends heavily on the use case involved. It depends on the the velocity of the events, how many attributes they have, how long you want to store it for. It depends on, with geofences, how complex they are, what kinds of processors you're using them in. So it's very, very hard to create a thorough matrix for all of these different use cases. I don't know that we have one that kind of addresses all those different aspects.
Yeah, it's difficult to, there's so many different permutations of things, but in general, if you're just doing pass-throughs in GeoEvent and not doing any analysis, we can handle up to about 4,000 events per second per node. If you're doing sophisticated spatial analysis where you might have thousands or tens of thousands of geofences that are moderately complex, 6, 8 edges or so, we can sustain over 2,000 events per second. And so if you chain, 15 tools together, obviously your mileage is going to vary a bit. So it's best to really do kind of a performance benchmark on your own for your use case that you have and the different analytics that you want to do. What we're seeing as a emerging trend since we've introduced geoanalytics is that folks are looking to simplify the streaming analytics of things and actually just pass the data into the big data store and then do more recurring geoanalytics on data. So instead of doing complex things like reconstruct tracks or other things in the stream itself, let's wait, actually get a couple minutes worth of data and then do a reconstruct tracks in the GeoAnalytics server. So we're starting to see a nice complement there where we can simplify the stream to just get the data into the server. I probably didn't answer your question completely, but come by our booth and we can walk through your specific scenario. Yeah, and if you have capacity planning questions, talk to our team. We're happy to help you guys capacity plan and give you guidance on how to start with that.
Yeah, I had a question. Is there a recommended input that is more efficient than others?
So the comment is, or the question is there an input connector that's more efficient than others? So not really. It's all a factor of the analytics that we're doing in the stream. So if you have TCP or HTTP or other things, TCP and WebSockets are going to be faster than if you expose like a REST endpoint or something of that nature. But there's not really depending on the adapters or anything like that, there's not really a significant performance difference.
I guess I'm talking specifically about big chunks of data like large CSV files.
Yeah, so for large CSV files, we have file connectors that are explicitly for that. And something new that we released is the ability to actually throttle the files in. So instead of just, if somebody drops in a file that has 1 million records in it, we used to just kind of choke on that. But now you can actually say throttle the data in at 2,000 events per second or whatever. And so that'll actually throttle that file in. We see that a lot in like vessels and other types of feeds that are like, here's a file of a whole bunch of things that happened in the last 5 minutes ago. And so that's a common use case there. I think we have to wrap the Q&A up here, but we'll stick around and answer any questions down at the bottom here. Thank you guys.
Thank you.